Hello everyone. In this video, we are going to see an example of a measurable function. In the previous video, we had seen and we had defined what a measurable function is. So let's take an example of this. Let's assume we have two measurable spaces. So let's say we have omega 1 and a sigma algebra on omega 1 defined as f1. Similarly, we have another sample space omega 2 and a sigma algebra defined on omega 2 as f2. Let's take an arbitrary sample space omega 1 to be, let's say, a and b. Let's say it contains only these two elements. And let's take a sigma algebra f1 to be the power set of omega 1. So it should contain all the subsets possible of omega 1. So f1 would be the set phi, because phi is always a subset, the set A, set B, and omega itself. So is f1 a sigma algebra on omega 1? Yes, it is, because since it's a power set, it would always be a sigma algebra on omega 1, and as it satisfies the three conditions. First one, that it's non-empty. The second condition of being a sigma algebra is that it should be closed under countable union. So if you take union of any of these two sets, it should also be present in f1. So take the union of, let's say, anything with phi, the null set would be that set itself, and this is present in f1. And similarly, if you take the union of any set with omega, that would be omega itself, and omega is also present in f1. Take the union of a and b, it would again result to be omega, and omega is in f1. Hence this is closed under countable union, and similarly the third property, closed under complement. So if you take any set present in f1, if you take the complement of that set, it should also be present in f1. So the complement of phi is omega, which is present in f1. So it satisfies the property. Complement of a is b. The complement of set b is a, and both of them are present in f1. Hence they too satisfy the property. And the complement of omega is phi, which is present in f1 again. Hence this is also closed under the complement. Hence you can see that f1 is closed under complement. Since it matches and it satisfies all the three conditions of being a sigma algebra, hence the power set of omega 1, f1, is a sigma algebra on omega 1. Okay. Now let's define the sample space omega 2 as well. So let's say omega 2 is the set 1, 2, where f2 is the power set of omega 2. And since it's a power set, we can define it like this. And omega 2. Okay. And similarly, we had seen that since it's a power set, so f2 is also a sigma algebra. So f1 is a sigma algebra on omega 1, and f2 is a sigma algebra on omega 2. Okay. Now let's define the measurable function on these measurable spaces. So the measurable function f, let's say we define it from omega 1 to omega 2. So this is the domain of this measurable function, and this is the range. Okay. And let's define f as, let's say, f of phi points to the null set in the sample set omega 2. This points to phi. Let's say f of a points to 1, f of b points to 2. Sorry, I have to write it in a better way. Yeah, this points to set 2, and similarly f of omega 1 points to the set omega 2. So we have defined f as this. So is f defined like this? Is f a measurable function? Let's see if it satisfies the property of a measurable function. So let's say we have this sample space omega 1 with the sets a, b, omega and phi being present in the sigma algebra of omega 1, and we have this sample space omega 2 with these sets 1, 2, let's say we have phi, and this is omega 2 itself. The circle is omega 2 itself, so we need not write omega 1 or omega 2 explicitly. Okay, so the function f points like this. So for a, it points a in the, for the set a in omega 1, it points to the set 1 in omega 2. For the set b in omega 1, it points it to the set 2 in omega 2. F of a, f of b, and for the set phi, it points to the null set in omega 2. And obviously for the whole set omega 1, it points to the set omega 2. So f is defined like this. Okay, now let's see whether it satisfies the properties of a measurable function or not. So we have to take any set present in the sigma algebra of omega 2, and for every such set present in the sigma algebra f2, its pre-image in the sample space omega 1 should be a part of the sigma algebra f1. So f2 contains phi 1, 2 and omega 2, as we have seen here, and so all the sets present in f2, if we apply an inverse function of the function f on them, they should give a pre-image in sample space omega 1, and that pre-image should be a part of f1. So let's check that out. So f of phi, f inverse of phi is nothing but phi. So if you do the f inverse of the null set here, it would point to this. And is this a part of f1? Yes, phi belongs to f1. As we can see here, phi is present in the f1. So yes, the pre-image for this exists. Okay, now let's see if the pre-image for this set exists or not. So let's take this f inverse of 1. What would this be? The f inverse of 1 would be the set A. So f inverse of 1 would point towards the set A, and this is the set A. And does the set A belongs to f1? Yes, we can see that this belongs to f1. This is a part of f1. Hence, since A belongs to the sigma algebra f1, we can say that the pre-image of 1 exists in the sample space omega 1, and that is present in the sigma algebra F1. Hence this satisfies the condition. Similarly, let's see if this satisfies the condition or not. You can easily see that this is the set B, and the set B is also present in the sigma algebra F1. Hence this also satisfies the condition. And omega 2, if we take a pre-image of omega 2, which will give us the set omega 1, and omega 1 is also present in F1. Hence the pre-image is present in F1. So this also satisfies the condition. Hence for all the subsets, all the sets present in F2 sigma algebra, if we take the pre-image of those sets, those pre-images exist in the sample space omega 1, and they are a part of the sigma algebra F1. Hence the F which we have defined like this, with domain of sample space omega 1 and the range of sample space omega 2, such that it maps like this, yes, in this case F is a measurable function. As it satisfies the condition of a measurable function. Thank you so much for watching the video. Hope you liked this video.